Hi everyone. This video we continue talking about polynomials, and more specifically we talk about something that is an important property or important characteristic of any polynomial, which is called zeros of a polynomial. Now, zeros of a polynomial, there's four different ways of thinking about it. These are all saying the exact same thing. When you say that a number c is a zero of polynomial, it's the same as saying that x equals c is a solution of if you set that polynomial equal to 0. Or you can say x minus c is a factor of that polynomial, or in terms of graph, c is an intercept of the graph of p. For example, let's say my polynomial is x squared minus 3x plus 2. Okay, and I tell you that x equals 1 is a 0. So what else does that mean? That also means that if I plug in x equals 1, gives me 1 square minus 3 times 1 plus 2, which is 3 minus 3 is 0, or p of 1 is 0. It also means that x minus 1 is a factor of px. Now, if I factor this, what do I get? Splitting the middle term, this is minus x minus 2x plus 2, which is x times x minus 1 minus 2 times x minus 1, x minus 1 times x minus 2, and in fact, x minus 1 is a factor. And lastly, if I plot this, finding the x intercept means we set this equal to 0. But from factoring, we know that this is actually x minus 1, x minus 2 equal to 0, giving me x equals 1 or x equals 2. And so, in fact, this is one of it is an x intercept. Okay, so this is why when you think of a 0, or another word for a 0 is root of a polynomial, then these are four things that are happening together. If it's a 0, then plugging that into the polynomial gives you a 0. And then also it means that x minus that number, x minus c, is one of the factors of the polynomial if you factor it. And lastly, that number c is also one of the x-intercepts for the polynomial. Now, this is an important idea because it helps us, again, it comes back to factoring and why factoring is important. Factoring helps us understand a lot of the properties of a polynomial. Now, here's an important result for polynomials called the intermediate value theorem. It's actually very intuitive. Here is the intuition behind the result. Let's say I have a graph, right, and I hide a certain part of the graph. Let's say I hide 2 and some areas near 2, but if I tell you that right before 2, so for x less than 2, all outputs are negative, and for x more than 2, all outputs are positive. Okay, if you know that for less than 2, all outputs are negative and then it becomes positive, then what you can say for sure is that however way you connect these, right, there are many hundreds of ways of connecting it, however way you connect it, there would be, it will have to cross 0. That's the idea. Or if you think about it, if you are going continuously from negative numbers to positive numbers, you have to go through 0. Okay. Or if you are hiking and your reducing in elevation and then increasing in elevation, at some point you would be at a flat surface. Or the other way around, if you're increasing in elevation and then you start decreasing, then you would have to be at the peak at some point. Okay, so the intermediate value theorem says, what it says is, given a polynomial px, right, and an interval a comma p, if p of x is negative for x less than a and positive for x greater than p, then px has a root in a comma p. Now, of course, these can also be the negative versions, negative, positive as well. Meaning it could be positive before and negative after. It still follows that it would be 0 in the interval. So this result helps us in a way guess or get close to what the 0 of a polynomial might be. Okay, and it's a 0 as a root or what we are calling 0 in that interval. Okay. Now, why is this all this root and zeros important is, let's try to understand how we can use them to plot this particular function. So in this case, it's already factored, right? So it is already factored, which means that just by looking at it, I can say that the roots are -2, 1, and 3. How? Well, if you plug this equal to 0, you solve the individual equations x plus 2 equals 0, x minus 1 equals 0, and x minus 3 equals 0. Otherwise, you just use the 4 equivalent definition and think of x plus 2 as x minus -2, so that c is -2 and each of these become roots. But since these are the roots, these are also the x-intercepts, which means that I have 3 x-intercept in this graph. There's an x-intercept at -2, there's one at 1, maybe make a more realistic -2, and one at 3. Okay. Next is endpoint behavior. Now, endpoint behavior, the highest power of x is x cubed, which means it is odd, right? It's odd and it's not negative. So that means that as x goes to positive infinity, y goes to positive infinity. And as x goes to negative infinity, y goes to negative infinity. They will have opposing behavior, and in addition, when you multiply a positive number 3 times, you're still positive, so you're here. And if you multiply a negative number 3 times, you're still negative. Which means that my graph is going to come in from this negative, cross this -2, go up, turn around, cross 1, turn around, cross 3, and end up here. Okay. Now there are some liberties here I took, which we're going to get to in a bit, about why is this the possible shape and not anything else. Okay. Because there's also a possibility that I could have done something like that. Yeah. So why not that? So we are going to learn that later. But for now, the important part is that it goes through these and you have the endpoints which give you the shape. Let's try this example. This is currently not yet factored. Right, so the first step is going to be factoring it. I notice there's an x squared common. Let me take out a negative x squared to get 2x squared plus x plus 3. That's negative x squared. I need a 6 and a, sorry, this got to be negative 3. All right, so I need the product to be negative 6 and sum to be positive 1. So I take 3 and negative 2, which makes it negative x squared, 2x squared plus, minus 2x plus 3x minus 3, negative x squared, 2x, x minus 1 plus 3x minus 1, negative x squared, 2x plus 3 times x minus 1. Okay, so I get that my zeros now are 0, negative 3 halves, and positive 1. So there's a 0, there's a negative 3 half, and there's a positive 1. Now, for the end behavior, I have an even power, so they are similar in their behavior, but there's a negative sign, so it goes to negative infinity. So both go to negative infinity, which means they are both over here. Now in this case, we're going to go through this, we're going to come back here, but here we're not going to go through, we're actually going to turn and get that kind of a shape. Once again, for now, focus on the fact that these are the endpoints and these are the roots. Now, as to question why it turned and didn't go through, that's in the next video. Okay. So the idea is to see that, well, once I know where the x-intercepts are and what the end behaviors are, I can plot the graphs. With an exception that I still need to know when it goes through and when it turns. Okay, that's it for this video. The next video we will fill in the missing part about when it turns and when it goes through, and with that we will be able to plot any polynomial function. That's the end of this video. Thank you.